Today's lesson is to look at systems of linear equations. And this is going to be a long video because I'm going to go through the whole unit right now. So along the way, we're going to define what a linear system is. We're going to look at 4 different ways to solve a linear system. We're going to look at how to verify our solutions algebraically. And we're going to create linear systems from real-world scenarios. And these goals are going to kind of be mixed and matched. So to begin our discussion, I've said write 2 equations for the scenario below. Mike took his class to an escape room. For 2 adults and 19 kids, it cost $384.50. Another group of 8 adults and 4 children arrived, and it cost them $278. What is the cost for each adult and each child? So as always with these videos, I'd encourage you to pause them and try these problems before I go through them. So with this, there's obviously 2 things we don't know. And in math, whenever you don't know something, it's good to represent that with some sort of variable. So x and y are common, but given the fact that we have adult and child, I'm going to use a and c. Okay, so if I look at this and I look at Mike's class first, well, I have 2 times the cost per adult, so 2a, plus 19 times the cost per child, c, and those 2 costs together equal $384.50. For this other group, it says 8 adults. Well, I'm going to take whatever the cost is per adult and times that by 8. And 4 children, so take whatever the cost per child and times by 4, and altogether that's going to equal $278. So what we've created here is a system of equations. 2 equations in this case, and they're linear equations because they both form straight lines. And if we had used x and y instead of a and c, I think that you may have more easily seen how they're straight lines. But whenever you have 2 variables, both to the power 1, it's going to form some type of straight line. And in this problem, we would want to be able to solve for both of those variables. And in math, you can never solve just one equation for 2 variables. You have to have 2 equations to solve for 2 variables. And so that is what the system is. And the solution to a system is the ordered pair, or in this case, it would always form an ordered pair on a graph where those 2 lines crossed. Okay? So in this case, if you went ahead and solved it, we could do a bunch of things for that. This one's a bit more complicated, so we're not going to start with this one. But you would find that 1 adult ticket, if you wanted to, would be $26, and 1 child's ticket would be $17.50. And so the ordered pair, 26, comma, 1750, would be the place where those 2 lines meet. So we're just going to take a minute and define a linear system so we can use this for the rest of this lesson. A system of linear equations is a set of 2 or more lines. There are quadratic systems, there are all sorts of systems. So whenever you see systems, it just means you have more than one variable where you're trying to solve a problem. But for this lesson, it's going to be entirely focused on straight lines. And the solution to a system is the xy ordered pair where those 2 lines cross. So for example, if I wrote out the equation x plus y equals 7. This is not a system because there are an infinite number of xy values that work for this equation. 1 plus 6, 2 plus 5, 3 plus 4, on and on and on. Okay? But if I went ahead and said below it x minus y equals, 3, now all of a sudden I have a system. I have 2 equations, I have 2 variables, and because I have both 2 equations and 2 variables, I can solve for both. And that's what we're going to start doing. I'm going to actually use this one system of equations to introduce you to all 4 methods that we will go through in this lesson. So The first method we're going to talk about is guess and check, or what some people call inspection. And with a system that is this simple, sometimes guess and check is literally the fastest way. And I think to myself, well, what two numbers added together make 7, but subtracted equal 3? Well, it won't take a whole lot of work if you do a bit of guess and checking to realize that when x equals 5 and when y equals 2, that is the solution. 5 plus 2 is 7, 5 minus 2 is 3. So we don't need to do any fancy algebra, don't need to graph any lines, anything like that. We can simply guess and check. And so I'm going to take a minute, erase this, and we're going to write out that solution. Okay, so we've got x plus y equals 7, x minus y equals 3, and our first approach that we can use is guess and check. Okay, I'd only use that on simple type of problems or on word problems where I actually don't have a clue how to get started. That can be a really, really effective approach. Second way we can do that, well, I've brought up a few times that these are lines, so we could go ahead and graph these lines. And if you've been part of this series of lessons from the previous unit, we looked at linear relations. Both of these lines are pretty quick to graph, and I'm not going to do tons of explaining, but I will graph them pretty quickly. Okay, so I would want to convert this into slope-intercept form, and I would do that by subtracting x from both sides on the top equation. And so whenever I have a system of equations, I label the top one 1 and the bottom one 2, just so I can keep track of them. If I ever rewrite them or do any sort of algebra, it helps me to keep track. So in this case, I'm rewriting equation 1 as y equals 7 minus x. Just subtracted the x. For this one, I might add the y to both sides and subtract 3 from both sides. And so I would get y equals x minus 3. Again, if you're struggling with graphing lines and manipulating equations, we did a decent amount of that in the last unit. So these are both lines, and if I went ahead and graphed them, well, this line, this bottom line, has a y-intercept of -3. Obviously, it is much better to use graph paper if you are going to go ahead and solve systems graphically. All right? But I'm going to start at -3, and I'm going to go up 1 over 1, up 1 over 1. And when I'm going ahead and solving systems, I'm going to draw a lot of points for that first line because I don't know where they cross. So I've drawn a series of dots. Obviously, because we guessed and checked this one already, we know where it crosses. All right? For this one, the y-intercept is 7, so I didn't draw it quite high enough. I need to go up to 7 on the y-axis. The slope is -1 now, so I'm going to go down 1 over 1, down 1 over 1. And I'm going to keep doing that until I find a place where they cross. And sure enough, graphing these, I noticed that they cross at the point 5, 2. Okay? So there's our second approach to solve this system. Now, some of you might say, well, we've already solved it using guessing check. Why are we wasting our time? I'm just taking some time to introduce you to the 4 methods that we'll be going through. And along the way, I hope that I can help you to see when it will be helpful to use graphing, when it will be helpful to use algebra, and when it will be appropriate to just guess and check. A third way we can do it is something called substitution. Now in math, if we have 2 equations, and I know that the ordered pair where they cross has to be the same. So in other words, in this case, x equals 5, y equals 2. We know that that's the point where they cross. Well, I can go ahead and substitute. Okay, so my third approach that we're going to be talking about in this lesson is something called substitution. Well, if y equals x minus 3, that means I can take this x minus 3 and I can substitute it in for y in my other equation. Now, if you're saying, well, why would I do that? Well, again, when I have one equation and two variables, I can't solve it. There's an infinite number of x and y values that work for the equation y equals 7 minus x, or the equation x plus y equals 7. But if I rewrite this as, instead of y, I'm substituting x minus 3 because they're the same thing, I can go ahead and say x minus 3 equals 7 minus x. And now all of a sudden, I have an equation that only has one variable. It only has x's. And I can always solve one equation for one variable. So if I go ahead and solve this, I might add x to both sides, because this is negative right now. So x plus x is 2x. And I might, so I'm going to add x to both sides. Again, I can only combine x's with x's and numbers with numbers. I'm going to add 3 to the other side. And so 7 plus 3 is 10. My negative 3 and positive 3 cancel out here. And then 2 times x, well, that means I'm going to divide both sides by 2. And I find out that x equals 5. Not a surprise, this is the third approach that we've done. Okay? Now, am I done? Never am I done when I've only found one variable. Because the whole idea of a system is I'm finding the ordered pair where they cross. So once I've found one of my variables, now I need to go ahead and solve for the other one. And in this case, I can use either equation because it's the point where they cross. So I might just use the top one and say, therefore, y equals 7 minus not x anymore, but 5. And 7 minus 5 is 2. So again, I've got the ordered pair 5 and negative 2. Finally, fourth approach. I'm going to go ahead and erase this. Fourth approach is actually usually my favorite approach when it comes to linear systems. Not when it comes to quadratics, I prefer substitution, but with linear systems, I prefer elimination most of the time. Okay. And I'm not going to get into the huge theory behind it, at least not right now. I might later, but what you do essentially with elimination is you look to add and subtract these equations in order to eliminate a variable. What do I mean by that? Again, I can't have two variables. I can't solve an equation for two variables. But since these are the same thing, let's say that I subtracted this from this side and subtracted this from this side. Since they're the same thing, I'm not changing the value of this original equation. So I'm going to go ahead and do that. I'm going to go ahead and subtract these equations from each other. And look what happens. X minus x is 0. Okay? Y minus y becomes plus y, so that gives me 2y. 7 minus 3 is 4. And I always put that second bracket in, or second equation in parentheses if I'm subtracting. Because I want to make sure I apply that negative to every term. At this point, now instead of having two equations with two variables, I have one equation with one variable. Which is beautiful because I can quickly solve this for y by dividing both sides by 2. Again, this number's familiar. We know the answer is 5, 2. In this case, we found y first. That means we have to go ahead and find x. And we would do that by taking this value and plugging it into either equation. Because now that we know one variable, we can use our original equations to solve for the other. So let's just say I use the top one, x plus 2 equals 7. Well, that means that x equals 5. So obviously, as we keep moving through this video and this lesson, we're going to look at more complex problems than this system of equations. But at this point, we have introduced all 4 methods that I know of when it comes to solving a system of linear equations. So as we start doing more problems together, we're going to have this conversation about which approach would make the most sense. So I've since solved the system y equals 2x minus 3 and y equals negative 1/3 x plus 4. And I don't know about you, but personally, I'm not super keen to guess and check when there's fractions involved. And if you're really comfortable with fractions, you might want to. Another thing that's important to note is if the solution to a system is a decimal, then guess and checking becomes extra challenging. If I'm looking to say, well, can I graph these? Well, hopefully at this point, if you're in my class, these two lines are very simple to graph. And the reason is they're both in slope-intercept form, just like the prior one. So if you want to pause this video and graph these, that's how I'm going to go ahead and solve it. So I'm going to draw a real quick XY grid. Again, I'm going to just do my best to make sure that these points are accurate, because otherwise I'm going to get an estimated solution. So with this one, my y-intercept is, of course, the number, the constant, the one that's not attached to the x, and that's -3. And my slope is 2, so I'm going up 2 over 1, up 2 over 1. And again, whenever I'm doing this, I'm putting multiple points on a graph at the same time. Okay? I don't know where that intersection point is going to be yet, so I want to have a few accurate points drawn. For the second one, my y-intercept is at 4, and my slope is -1 over 3. Well, whenever I have a negative slope, it goes down, so that means I'm going to go down 1, right 3, down 1, right 3, and lo and behold, I have a very quick point to identify. It is the point 3, 3 as my solution. Now, we're going to take this opportunity to check our answer, because in math, one beautiful thing is that you can always check your answers. You don't have to ask, hey, is this right? Most of the time, when it comes to algebra, you can check it yourself. And how do we do that? Well, if this is the ordered pair where these two lines really cross, and I haven't messed up how I graph them, then when I take 3 for x and punch it into either equation, it should tell me that y equals 3. So let's do that. Let's go ahead and check this. Well, y equals 2 times 3 minus 3. Well, 2 times 3 is 6, minus 3 is 3. Which means that this line, 2x minus 3, definitely goes through the point 3, 3. I just confirmed that my drawing was correct. For this one, a little bit harder, but not that much harder. So y equals -1/3, and instead of x, I'm going to punch in 3 plus 4. Well, -1/3 of 3 is -1, plus 4 is 3. So again, we found out that when x is 3 in this one, y equals 3. So therefore, we have now confirmed or verified algebraically that our answer is correct. So again, more than just, hey, I have the strategies, tell me which one to use. I want us right now to start thinking about which situation or which of these approaches might work for this, even though you haven't seen very many examples of all the different types. So guess and check. Do I want to pick values for x in this equation and find out what y equals and then see if that also works for my second equation? Heck no, not a chance. But when I look at this top equation, it looks familiar to me. That's that slope point form that we looked at last unit. And so when I see something in slope point form, I think, yes, I am ready to graph that right now. Okay, so I'm going to again graph this one because this is not a really fun form to do any algebra with. If I wanted to use substitution, I'd have to get rid of the brackets, get a bunch of fractions. No thank you. But this graph is not really well drawn, but we will make do with it. And one reason I'm confident I can make do with it is because, again, I'm putting lots of points down. And so that helps me to just kind of guide my line. Even if it ends up looking crooked on the screen, I know that my points are going to be accurate. Okay? So first thing I do is identify the point it passes through. Well, if I see a +6 and a +7, that means that the point it passes through is actually -6, -7. Again, check out that slope point form video if you're not sure about that. So that means I'm going back 6, and I'm going down 7. I've got a point there. Okay? And my slope is 3 over 5. So that means I'm going up 3 and over 5. And so that's going to end up right there. I'm going up 3 and over 5. And so I've got 2 more points that I've drawn. Okay? One at -1, -4, and one at 4, -1. All right? And I'm going to go ahead and connect those like so. Hopefully that'll be enough for the solution. Now this is written in general form. Not super pretty, not a big fan, but I can convert it, if I have the algebra skills, into slope-intercept form. Okay, and that's what I usually do when I'm graphing a line. Slope-intercept form, y equals mx plus b, is the best for me. And the way I'm going to do that is I'm going to pull that 3x onto the other side by minusing it. And I'm going to also pull that -10 over by adding it. And so I've got 2y equals -3x plus 10, which is not done. I need to get y by itself, and the way I do that is by dividing both sides by 2. So I get -3 over 2x, and I need to divide everything by 2, so I get plus 5. So I'm going to go up 1, 2, 3, 4, 5 on my y-axis, because that's my y-intercept, and I'm going to go down 2 and over 3. Or probably down 3 and over 2. Down 3 and over 2. And lo and behold, I have my intersection point. So the only ordered pair that if I punched in for x and y into both equations that would work would be the ordered pair 4, -1. I'm going to quickly check it here. 3 times 4 is 12. 2 times -1 is -2. 12 minus 2 is 10. 10 minus 10 is 0. So I know it works for the one equation. I don't really feel like checking it right here, right now, but I assure you it would work. So we've looked at now 3 examples where we graph. We're going to move away from graphing. So if you're hoping for a bit more practice or you need to stop and take a second to look at graphing, now's the time to pause. We're going to start diving into some substitution and elimination questions, or questions that are more geared for those methods. So for this problem, and for any problem, you can graph it. I wanted to make that clear. And we could use guess and check if we wanted to. We could try and find values for x and y that work for this one. For example, 8 and 1, I quickly see 4 times 8 is 32, plus 1 is 33. But then I'd have to go ahead and check to see whether that worked for the top equation. And in this case, it doesn't. So guess and check can be time consuming. Now, we are going to be spending some time looking at how to do algebra, how to not graph anything. So for those of you who hate graphs, this is beautiful. And I'm going to start with the one I dislike a bit more, all right? And it's substitution. And the biggest thing you want to look at if you're using substitution is you need to isolate one of these 4 variables. Isolate just means get by itself, okay? So for substitution, I'm going to actually write that out because that's the key point. Isolate x or y in either equation. Now, are there slight tricks sometimes? Yeah, but I don't find they're ever needed because if we know how to use elimination, those situations aren't really relevant. So, is there one of these variables that is easiest to get by itself? Well, absolutely. This y is the easiest to get by itself, and we can do that by just minusing 4x from both sides of the equation. So again, y equals 33 minus 4x. Okay, and again, that does not become 29x because you can only add and subtract terms that have the same variables raised to the same exponents. Okay, so this is my equation 1, and this is my equation 2. Yes, it's rewritten, but it's still from equation 2. Now, in order to use substitution, we now need to take whatever that y is, and we need to substitute it into our other equation. Okay? So, substitute isolated variable into the other equation. If you put this back into equation 2, all you'll find is that 33 equals 33. Everything else will cancel out, and you'll be like, well, I don't even have any variables. Okay, so what do I mean by that? This might not make a ton of sense to you. Let's do it. We're going to take 33 minus 4x, and we're going to replace y with 33 minus 4x, because they are equal to each other. Okay, and so instead of having an equation with two variables, check out what happens. 5x minus 7 times 33 minus 4x equals 66. Okay? We've gone from an equation that has two variables to an equation that only has x's. And we can always solve an equation with one variable. Okay, so I'm going to have to do a bit of math. I multiply before I add and subtract, so I'm going to leave this 5x alone. Negative 7 times 33 is negative 231. Negative times a negative is a positive, and 7 times 4 is 28x equals 66. Now at this point, lots of ways to do it, but I'm going to combine what I can. On this side, I got 33 x's right here. Okay? And at the same time, I'm going to get that negative 231, and I'm going to put it on the other side. So I'm going to add 231 to both sides of this equation. And when I add 231, that gives me 297. Now, almost done. 33 times x, so the opposite of that is divided. So I'm going to divide both sides by 33, because I can't do one thing to one side and not the other. And I'm going to get x equals 9. Now again, we are not done until we have an ordered pair. Okay, so some of you might find it valuable just to write out an ordered pair at the start of every question to remind yourself, hey, okay, I found x, that goes first, I have to find y. And the beautiful thing about substitution is, since you have to isolate one of the variables, it's always going to be pretty easy to find the second variable. Okay, so I guess I can just say solve for leftover variable. That's what we did when we solved for x. It was the variable that was left over. The y's were gone, and then at the end, now we need to solve for second variable, okay? Because we need an ordered pair. So for those of you who like notes and like tips and all that stuff, there you go. All right? So y equals 33 minus 4 times, not x anymore, times 9. We know that x equals 9, if we've done our math correctly. Well, 4 times 9 is 36. 33 minus 36 is negative 3. And so there is how we could use substitution to solve a linear system. Okay, so once again, we've got a system. We could graph it, we could use a guess and check. But we're going to use substitution. And by the end of this whole lesson, you might look at a question like this and think, I'd rather use elimination. But it is kind of set up for substitution. All right? And the reason why is, again, we have variables that have a coefficient of 1. And that's the key. If you don't have any coefficients of 1, I personally would always avoid substitution. All right? And that's because I'll show you how to use elimination in a minute. But pause this video, give this a try. It's very similar to the last one. So it doesn't matter which one we solve for. I'm going to just choose to solve for x. And the way I'm going to do that is I'm going to minus y from both sides. So x is going to equal 1 minus y. From this point, now that I have my isolated variable instead of x, now I'm going to replace it in the other equation, in this case in equation 1, with 1 minus y. Okay, that's the substitution. That's why it's called substitution. So instead of 3x, it's 3 times 1 minus y. Minus 5y equals 43. And again, I just need to make sure I follow order of operations or bread mass at this point. So I've got brackets, nothing I can do there. I can't combine 1 and negative y, but I can multiply. 3 times 1 is 3, minus 3y minus 5y equals 43. I always look to combine what I can. So negative 3y minus 5y is negative 8y. I'm going to get my y by itself by subtracting 3 from both sides. So negative 8y equals 40, and that's key. I see a lot of students drop the negative sign in front of that 8. That is attached to that 8. Okay, it's a negative 8y or minus 8y, same deal. And anytime we have a number in front of a coefficient or in front of a variable, we, to get rid of it, divide by that number. So in this case, we are going to divide by negative 8. If I do it to one side, I need to do it to the other side. So y equals 40 divided by negative 8, which is negative 5. So in this example, we've actually found y first. So if I were writing out my ordered pair, make sure it goes second. And again, the beauty of substitution is, once I found one variable, I have a variable that's already isolated to find the other one. So I'm going to say, therefore, that's what those 3 dots mean, x equals 1 minus negative 5. Well, 1 minus negative 5 is 1 plus 5, or 6. And so the ordered pair, the place where these 2 lines would cross on a graph, is 6, negative 5. But I know that my graphing this line would actually be kind of complicated because my y-intercept would not be a clean whole number. And so I might need to be a bit very precise when I'm graphing it. So another reason that knowing some algebra approaches is helpful. So the moment we've been waiting for. What's this final approach that I've referred to a few times? I've shown you once in that simple example at the start. We'll be a bit more thorough as we look at these examples. So the first example, 2x minus 6y equals 15, and 7x minus 2y equals 5. First of all, it's not easily graphable. Yes, we could convert it into slope-intercept form, but I'd get some decimals for my y-intercepts. Guess and check, not super keen to use that either. And substitution is not my friend here because none of these have a coefficient of 1. Could I solve and make them 1? Yes, I could, but I'd get fractions or decimals in the process. I don't want that. All right, so elimination is my favorite approach when it comes to solving systems. And the way you start elimination is you have to get either your x coefficients or your y coefficients the same. And so I'm going to write that down, kind of like I gave you a few bullet point tips for substitution. Here are my bullet point tips for elimination. Get the coefficients, and again, that's a number multiplying to a variable, or the number in front of a variable. Get the coefficients of x or y, and I'm going to underline the word or. Does not matter. The same by multiplying one or both equations. You're saying, well, how can you multiply an equation? Well, if I, let's say, tripled this bottom equation, I haven't changed its value. If I times one side by 3 and the other side by 3, it's the same equation. So I can do anything to an equation as long as I do it to both sides. And so the question is it easier to get my x's the same or my y's the same? And to me, I think it's much easier to get my y's the same. Simply by multiplying this by 3 or by negative 3. Okay? And I'm going to actually multiply it by negative 3, and I'll show you why in a minute. All right? So if I multiply everything by negative 3, negative 3 times 7 is negative 21x. Negative 3 times negative 2y is positive 6y. And negative 3 times 5 is negative 15. Again, I have to multiply every term by whatever I choose. Okay? And I'm going to still write this 2x minus 6y equals 15 Wouldn't matter if it was the top or the bottom. Now, the next thing we do is we add or subtract. And it does matter which you pick. Okay? Add or subtract the equations to eliminate x or y. All right, so this is my little helpful guide. Hopefully it's helpful. Well, the question is, we got the coefficients of y the same. If I add these, are they going to become 0? Or if I subtract them, are they going to become 0? And the answer is if I add them. If I add these equations. And that's why I chose -3. Because whenever I can add something, it's just easier in my mind than subtracting. I don't have to remember about double negatives or anything like that. Okay, so -6 plus 6 is nothing. 2 plus and minus, well, that's the same thing as just subtract. So -19x. Okay? 15 plus a -15, well, that's easy. That's 0. And so if I divide both sides by -19, x equals 0. Beautiful. That means that these guys cross at their y-intercept. Okay? I'm not done. I have to find y. And this is the one thing I dislike about elimination. Finding the second variable is harder than substitution. Okay? Not probably in this case, but in most cases. So we can solve for leftover variable, just like in substitution. What do I mean by that? We solved for x right here. It was our leftover variable. We eliminated our y's. X was left over. That's our leftover. Okay? And then now we need to solve for our second variable. Because in every question we've done today, every problem we've done today, we have needed an ordered pair. Okay? And if you're wondering how, just use either original equation. I'm going to use the top one. 2 times 0 minus 6y equals 15. 2 times 0 is nothing. Again, I'm going to make sure I keep that negative attached to the y. And I'm going to divide both sides by -6. And y is going to equal -2.5. So my ordered pair is 0, comma, -2.5. We're going to take on another problem using elimination right away here. Before we tackle a more challenging elimination problem, I thought it would be valuable to look at this one, just to make sure everyone has a firm base of when elimination would be ideal to use. I said get the coefficients of x or y the same by multiplying one or both equations. I should have said if necessary, because sometimes it's not even necessary. In this case, the coefficients of x are already the same. So I can right now go ahead and make a decision about whether I need to add or subtract. And in this case, 3 minus 3 is 0, and that's what I'm looking to do. I have to eliminate, so therefore I'm going to subtract everything. Okay? So 3 minus 3 is nothing. -4 minus -2 is -4 plus 2, which becomes -2y. And 1 minus -1 is 1 plus 1, which is 2. Go ahead and get y by itself. That's our leftover variable. By dividing both sides by -2, and I get y equals -1. Again, tailor-made for elimination, because none of these variables have a coefficient of 1, so substitution would be pretty ugly. Okay. Now take this and plug it in to either equation. Doesn't matter. I'm going to use the top one because they look very similar to me. And now all of a sudden I just need to go -4 times -1 is +4. I need to get x by itself by subtracting 4 on both sides and then dividing by 3. And so I get the ordered pair -1, -1, which is always my goal when I'm solving a system of equations. Now we're going to tackle a slightly more challenging one. Okay? And again, I'd really encourage you to try this out before I go through it. Okay? So we've got 6x minus 2y equals 21. And we have got 4x plus 3y equals +1. Again, not set up for substitution. I'm not really wanting to use guess and check. And while I could graph it, I do see that the y-intercepts are going to be pretty gross. So I am going to use elimination, which means I have to get my x's the same or my y's the same. And, well, my y's are a smaller number, so I'm going to go ahead and get them the same by looking for that common multiple. What's the smallest number that 2 and 3 go into? It's 6. So I'm going to multiply this by 3, and I'm going to multiply this by 2. All right? And I also picked the y's because I saw their signs were different. And when the signs are different, we are going to add. When the signs are opposite, and when the signs are the same, we are going to subtract. And I don't want to subtract. So I'm going to multiply this top equation by 3, get 18x minus 6y equals 63. Again, have to multiply everything by that number. I'm going to go 2 times 4 is 8, 2 times 3 is 6, and 2 times 1 is 2. All right, so I pause and I say, are my coefficients the same? The answer is yes, which means I can now go ahead and add those equations because the signs are different. And 18 plus 8 is 26x. My y's are eliminated, so now I'm going to be able to solve for my leftover variable by getting 26x equals 65. I'm going to divide both sides by 2, and when I do that, I get 2.5, or 5 halves. Again, my only dislike about elimination is that finding that second variable can be a bit more tricky. Not too tricky. I'm going to use this bottom equation. 4 times 2.5 plus 3y equals 1. I know that 4 times 2.5 is 10 plus 3y equals 1. And then the same deal. I'm just looking to get y by itself by getting those numbers gone. Plus 10, I'm going to cancel it out by minusing 10. And so I'm left with 3y equals -9. And then to get y by itself, I need to divide both sides by +3. And that gives me a y value of -3. So the ordered pair where these guys cross is 2.5, comma, -3. So at this point, I hope that we've gone through a lot of examples. I hope you're getting more confident at being able to look at equations and say which approach would be most appropriate when it comes to solving the system. Because in the end, every one of those approaches yields the same result. An ordered pair that if we wanted to check, we could punch in and confirm that it works for both equations. For this problem, it says if one line in a system is y equals 3x minus 4, write the equation of a line that would yield no solutions. So at this point, hopefully you know what a system of equations is, and you know what the solution to a system of equations is. It's the ordered pair where those lines cross. So what kind of lines would produce no solutions? Well, they'd be 2 lines that never cross, which in our prior unit we looked at, those are parallel lines. Well, what do we know about parallel lines? Parallel lines have the same slope, but a different y-intercept. So in this case, we could go y equals 3x minus 8, or 3x plus 17. Wouldn't matter what we picked for this, as long as it was parallel and had the same slope. What if it yielded an infinite number of solutions? Okay. Well, the solution to a system is where they cross, and they're crossing an infinite number of times, well, there's only one answer that we can put here, and that would be the exact same line. I mean, you could put 6 over 2, I guess, or something like that, but it'd be the same line. What about if I said one solution? Well, the thing that holds these two together is that they both have the same slope. And we know that if they have the same slope, they're either never going to touch or they're always going to be touched. If I'm looking for one solution, it will be any other line that doesn't have a slope of 3. So I could pick literally any number I wanted as long as I didn't pick a slope of 3, because that, I know, would eventually have lines that go ahead and cross. So you will notice that sometimes lines produce no solutions or an infinite number of solutions. And I want to just quickly touch on what happens with this no solutions if you start falling in love with, let's say, elimination. All right? So let's take this system that we just made up, y equals 3x minus 8 and y equals 3x minus 4. My hope is you'd be able to look at those and say, oh, they're parallel, they're not going to touch. But sometimes, we all know it, we get into that tunnel vision of math. I'm doing what I'm doing elimination, or I'm doing substitution, or whatever. Let's say we used elimination here. Let's see what happens. Well, my coefficients are already the same, so I'm going to go ahead and subtract. Y minus y is nothing. 3x minus 3x is 0. And negative 8 minus minus 4 is negative 4. Notice how both of my variables eliminated. Okay, so we'll come back to that in a second. Let's look what happened with an infinite number of solutions. If I went ahead and wrote my other equation, and I used elimination, let's see what happens here. Y minus y is 0. 3x minus 3x is 0. Negative 4 minus minus 4 is 0. So again, both variables cancel out. But the difference is this statement is never true. So that's why there are no solutions. This statement is always true. 0 equals 0 always. Therefore, that indicates an infinite number of solutions. For this last section of our odyssey through systems of linear equations, we're going to look at how do we create or set up systems of equations when we're given word problems. We're going to go through 3 questions together of increasing difficulty, at least in my opinion. And I encourage you to pause the video and try to set up the systems on your own. We're not going to solve all of them, but I might give you a couple tips. So the first one says Frank has saved $21.40 for a new toy, consisting entirely of dimes and quarters. If you don't live in Canada, a dime is 10 cents, quarters 25 cents. How many of each coin does he have if he has 103 coins in total? So for me, first thing I do is I always read the question, because the question often will tell me what my variables are going to be. Before I start solving, I want to identify what they represent. So in this first one, it says how many of each coin? Well, that means that Q is going to be the number of quarters. That's one thing I don't know that I'm asked to find. And D is the number of dimes. Putting the number of just reminds me that I'm looking at a total quantity. So the number of quarters plus the number of dimes, Q plus D equals 103. Now again, there'd be a decent number. There'd be 103 possibilities that could work for that. I'm wondering, is that 103 or 104? I guess there'd be probably 104 possibilities. But there'd only be one that would also give that total when it came to the value. Okay, and so if I'm trying to create money, it's going to have to equal $21.40. So I'm going to have to take an amount and turn it into money. Well, the way I turn quarters into money is by multiplying however many quarters I have by 25 cents, 0.25. I could also write that as over 4. And by taking every dime that I have and multiplying it by a tenth, or 0.1. That would be the quickest way to set up that system. Obviously, from here, this is a bit different, perhaps more complex than the ones we've done in the past. So if you aren't sure how you'd move forward on this, you could either look to change that, or both, to a whole number. For example, if I times this entire equation by 10, it would turn this into a whole number, okay? And that would become 2.5 cubed plus d equals 214. And all of a sudden, I have a system that would be very set up to use elimination. For this next example, it says Tim invested $7,000. Some at a 6% interest rate and some at a 9% interest rate. If the 6% investment earned half of the interest of the 9% investment, how much was invested at each interest rate? So, of course, feel free to pause the video and give this a try. First thing we always want to do is look at the question and see if that can reveal what our variables represent. And in this case, I'm going to just call this investment A, and that's the money invested at 6%. And we'll call B the money invested at 9%. Okay, because again, the question is asking how much was invested. And usually we can get one easy equation out of just setting up our variables. It tells us that the total amount was 7,000. Therefore, A plus B, the amount invested in the first and the amount invested at the second, totals up to $7,000. Fantastic. Now we need to use this interest stuff and the interest earned. Okay? And the key word that's kind of hidden here is half. Okay, so if I'm earning 6% on an investment, that just means that if I invested $1,000, I would earn 6%, that's $60. Okay, so I'm going to take 6%, and whatever amount I invested in investment A, I'm getting 6% of it. And I need that to somehow equal, because I need to set up an equation, the amount of interest earned at 9%. So 9% of investment B would be 0.09 times B. Now, I know this isn't right yet, because it doesn't say that the interest earned on the 6% equaled the interest earned at the 9%. What it's saying is that this was half of this. So in order to make them equal, which one do I need to double? Hopefully you're seeing that this is the one I need to double, because right now it's half as much. So in order to make it equal, I would double it. Now, some of you might be wondering, well, where do you go from here? Well, if I wanted to use substitution, the first thing I would do would be to isolate either my A or my B. Okay? If I wanted to get A by itself, I would just divide both sides by my coefficient, 0.12, and therefore I would get 3/4 or 0.75 times B, and then I could substitute that in for A and get on my way to solving this problem. I could also use elimination, but that would take a bit of work, getting one of my two coefficients the same. For this last word problem, we're not only going to set it up, we're going to solve it, because I realized that I haven't done an example during this lesson on how to deal with fractions, and this one, fractions will appear. So again, pause it if you want to give it a try. It's a tricky one. So it says a cyclist road test involves uphill and downhill sections. Tate averaged 20 kilometers per hour on the uphill sections and 40 kilometers per hour on the downhill sections. If you completed the 35-kilometer course in 1.3 hours, what is the distance of the downhill sections? So like I've been telling you, often the question will reveal to us what we do and don't know. But in this case, it's not actually the case. Another thing that is that we need to be careful of is we can't assume that the uphill and downhill sections are the same length, which I see some students do. So one thing you need to understand when you see these speed, distance, time type of problems is there's a pretty famous triangle that kind of just, if you ever forget the relationship between those three variables, that speed, how fast you're going, is the same as distance divided by time. And that triangle can help you because if, let's say, you're looking for the speed, it equals distance divided by time. If you're looking for time, it equals distance divided by speed. And if you're looking for distance, that equals speed times time. So that's a little triangle I draw when I get these problems because it just quickly reminds me the relationship between these three variables. And when I look at this problem, I see time, I see distance, and I see speed. Okay? Now, what I am going to do is I am going to say, I'm going to start with this. And sometimes this is how I think through it. I say that the time of the uphill section, so I just put t with a little subscript u, plus the time of the downhill sections equals 1.3 hours. Now you might look at that and say, well, that's not very helpful, and you're actually right. Currently it's not very helpful. But I do see information about the distance, okay? Pardon me, about the speed, and I don't know much about the distance. So what I know about time is that time is the same as distance divided by speed. Okay, well, the distance of the uphill sections divided by the speed of the uphill sections is the same as time. Plus the distance of the downhill section, so I'm just doing d with a little subscript d, over s of the downhill sections equals 1.3. Because time is the same as distance divided by speed. Okay? Now that looks more complicated than before, but the nice thing is I can fill in these things. I am looking for the distance, so I'm going to call that x. And I know the speed of my uphill section was 20, so I've got x over 20. Now, what's the other thing I don't know? I don't know the distance of the downhill section, so I'm going to call that y. And I know the speed of the downhill sections was 40 equals 1.3. Great. Now I have one of my two equations. Okay, and I have my x and my y. And at this point, I'd probably say, okay, x equals distance of uphill, and y equals the distance of the downhill. Just to remind myself. Okay? Still need to make another equation. Well, if x is the distance of the uphill and y is the distance of the downhill, and the whole course is 35 kilometers, that would mean that x plus y would equal 35. So there are my two equations. Now, I said that we'd also solve this one just to give you a sense of how, a reminder of how we deal with fractions. When we were doing elimination, we discussed that we could multiply in either one or both equations by something to change the coefficients. Well, I hate fractions, so if I want to get rid of these fractions, I'm going to multiply by the lowest common denominator, which is 40. Okay, so if I multiply every numerator by 40, times by 40, times by 40, times by 40, again, I need to do it to both sides. I'm just going to draw an arrow up here. Well, 40 divided by 20 is 2. 40 divided by 40 is 1. And 40 times 1.3 is 52. And I'm going to bring this second equation up here. X plus y equals 35. And all of a sudden, I've got an equation that's, yes, substitution would be nice, but elimination is right there for us. If we go ahead and subtract these equations, we see 2x minus x is 1x, y minus y disappears, and I'm left with x equals 17, which means the distance of the uphill sections is 17 kilometers, and thus the distance of the downhill sections would be 18 kilometers. So I hope this long lesson has given you a pretty comprehensive picture of how systems of linear equations work. I hope that you have more confidence when it comes to solving them, whether that be algebraically or graphically. I hope that you have a bit more confidence in terms of setting them up. And I hope you have a few strategies about which method might be appropriate given what type of problem you're given off the start. Thanks.